What is gravity made of? Before the first star burned or the first atom formed, something was already at work, quiet, invisible, and relentless. It bends light, shapes galaxies, holds your feet to the earth, and guides the motion of the moon. We call it gravity. But here is the unsettling question: what is it actually made of? Welcome. I'm glad you're here. Gravity feels familiar because we live inside its embrace every moment. Yet when physicists describe the universe at its deepest level, through quantum fields and curved spacetime, gravity becomes the great exception. The other forces arise from particles and fields we can describe with remarkable precision. Gravity resists that clarity. It shapes the architecture of the cosmos, but its own substance remains uncertain. Why explore this mystery? Because understanding gravity means understanding the foundation of reality itself, how space and time behave, how black holes form, how the universe began. It is not just an abstract puzzle, it is a doorway into the structure of existence. In this journey, we will gently unfold the ideas that scientists have built, from Einstein's insight that gravity may be geometry, to modern attempts to uncover its quantum nature. Step by step, we'll examine what gravity might be made of, and what that answer could reveal about everything else. Let's begin. We've been using gravity our whole lives. Nobody knows what it is. Close your eyes for just a moment and listen. Somewhere nearby, something just fell. Maybe it was a pen rolling off a desk. Maybe it was raindrops tapping against a window. Maybe it was just the quiet settling of a house as the day begins. Whatever it was, something was pulled downward. Something surrendered to a force so familiar, so constant, so utterly ordinary that most of us stopped noticing it before we were 5 years old. And yet here is something that might genuinely surprise you. Something that might make you set down your coffee and think for a moment. The scientists who study the universe for a living, the men and women with their names on Nobel Prizes and their equations written on chalkboards at places like Harvard and Cambridge and the Institute for Advanced Study in Princeton, those brilliant people cannot tell you what just happened when that thing fell. They can measure it with breathtaking precision. They can predict it so accurately that they used it to land a spacecraft the size of a car on a planet hundreds of millions of miles away. But if you walk up to the world's greatest physicist and ask him sincerely what gravity actually is and what it is actually made of, he will pause. He will likely smile a little. And then he will tell you honestly that nobody knows. That is what we are going to spend the next 3 hours exploring together. Not with math, not with confusing diagrams, just with ideas, told as plainly and as honestly as they deserve to be told. Because this question, this deceptively simple question of what gravity is actually made of, turns out to be the deepest question in all of science. And the journey toward its answer takes us through some of the most beautiful, most surprising, and most genuinely strange territory that the human mind has ever explored. So let us start at the very beginning. Let us start with your morning. You wake up. The blanket feels heavy across your body because gravity is pressing it down onto you. You sit up and your body takes effort to rise because gravity is pulling it back toward the mattress. You walk to the kitchen and the coffee you pour settles perfectly flat in the bottom of your mug because gravity pulls every molecule of liquid to the lowest possible point. You look out the window and see rain falling straight down, not sideways, not upward, but always, always down. You have lived inside this force every single day of your life. You have never once escaped it, not even for a second. Even when you jump, gravity is already reaching up to pull you back before your feet have left the ground. And here is the strange and wonderful thing. We have been living inside gravity for our entire lives, and we have treated it like wallpaper. We notice it when it inconveniences us, when we drop something and it breaks, when we fall and we hurt ourselves. But we never really stop and ask the deeper question. We never really sit with the full weight of the mystery. Think about the other things we interact with every day. If you ask someone what light is made of, a physicist can actually tell you. Light is made of tiny particles called photons, and they travel in waves, and we understand them so well that we built lasers and fiber optic cables and smartphone screens all on the back of that understanding. If you ask what electricity is, we can tell you. It is electrons moving through a material, and we understand that well enough to build the entire modern world on it. If you ask what matter is made of, we have an answer for that too. Atoms. And inside atoms, protons and neutrons and electrons. And inside protons, even smaller things called quarks. We go deeper and deeper and we keep finding answers. But gravity? When you try to go deeper with gravity, you hit a wall. A beautiful, mysterious, incredibly frustrating wall that has been sitting there since the beginning of science and has not moved an inch. And that wall is what makes this question so exciting. Because for the first time in hundreds of years, we are genuinely, seriously, tantalizingly close to understanding what lies on the other side of it. To understand why this question is so hard, it helps to appreciate just how long it has been asked. Let us go back to the year 1666. England is in the grip of a terrible plague. The universities have closed and sent their students home. A young man named Isaac Newton, just 23 years old, has gone back to his family farm in the English countryside to wait out the epidemic. And sitting there with nothing to do but think, he began to ask the question that would define his life. Now, the story of the apple falling on Newton's head is probably a legend. Newton himself mentioned the apple, but not the head. What we know is that while sitting in his garden, watching things fall, he began to wonder something that sounds almost childishly simple. He wondered whether the same force that pulls an apple to the ground might be the same force that keeps the moon going around the Earth. Before Newton, almost nobody had connected those two things. The moon moving in the sky seemed like something entirely different from a rock rolling down a hill. The heavens and the earth seemed to operate by different rules. But Newton had a hunch so powerful it would change the world. He sat down and did the mathematics. He calculated what kind of force would be needed to keep the moon in its circular path around the Earth. And then he calculated the force pulling things to the ground here on Earth's surface. And when he scaled the numbers carefully, accounting for the fact that the moon is roughly 60 times farther from Earth's center than the apple on the tree, the numbers matched. Beautifully, precisely, unmistakably. The force pulling the apple and the force holding the moon were the same thing. Gravity was universal, not just an earthly phenomenon, but a cosmic one. Every object in the universe, Newton concluded, pulls on every other object, always. The apple pulls on the earth just as the earth pulls on the apple. We just do not notice the apple pulling back because the earth outweighs it by an almost incomprehensible amount. This was one of the greatest insights in human history, and Newton knew it. But here is the part of the story that does not get told often enough. Newton was asked, repeatedly and insistently, by other scientists of his time, "All right, Isaac, you have described how gravity behaves, but what is it? How does the Earth reach across empty space and pull on the moon? What is the mechanism? Is there some kind of invisible string? Some kind of fluid filling all of space? What is actually happening?" And Newton, who could have speculated, who could have offered some plausible-sounding story, chose instead to do something remarkably honest and remarkably humble. He said in Latin words that translate roughly to this: "I do not frame hypotheses." He refused to guess. He said, "The mathematics works, the predictions match reality, and I will not pretend to know what I cannot know." The underlying nature of gravity, the machinery of it, was beyond what he could honestly claim to understand. That was in 1687. That was more than 350 years ago. And the honest answer today, from the finest physicists alive, is not so very different from Newton's. We know enormously more about how gravity behaves. We have a far deeper and more beautiful theory of it than Newton could have imagined. But what gravity is fundamentally made of at its deepest level is still, genuinely, an open question. Now you might be thinking, surely after 3.5 centuries of progress, with particle accelerators and space telescopes and quantum computers, surely we must be close. And the answer is yes. We are closer than we have ever been. The theories being worked on right now in physics departments around the world are, in the judgment of many brilliant people, within striking distance of an answer, but we are not there yet. And the reason we are not there yet is one of the most fascinating stories in all of science. Think of it this way. Imagine you are trying to understand a beautiful and complex piece of music. You can hear it playing, and you can write down exactly what notes are being played, in what order, and how long each note lasts. You can write it all down in musical notation so precisely that someone could reproduce it perfectly. That is what Newton did. He wrote down the score of gravity so perfectly that we still use his equations to fly spacecraft today. Now Einstein came along and said, "Wait, I understand not just the notes, but the instrument. I understand the structure of the thing producing this music." And he revealed that the instrument was space-time itself, bent and curved by mass, and that gravity was simply the shape of that instrument. That was a far deeper understanding. We will spend a great deal of time on that shortly. But here is where we are today. We know the score beautifully. We have a pretty good understanding of the instrument, but we do not know what the instrument is made of at the atomic level. We do not know whether it has a grain structure, a quantum structure, a deeper architecture underneath. And until we know that, we cannot say we truly understand gravity. That is our journey today. We are going to go from Newton's orchard all the way to the cutting edge of modern physics. We are going to meet ideas so strange they will make you blink. And we are going to arrive 3 hours from now, not at a neat and tidy answer, because science does not always offer those, but at a genuine and honest understanding of where we stand and what might be just around the corner. And I promise you this: by the time something falls again in your presence, you will never hear it the same way. Let us spend some time with Newton's gravity because it deserves it, not just because it was brilliant, which it was, but because understanding exactly where it succeeds and exactly where it fails is the key that unlocks everything that comes after. Newton gave us one of the simplest and most powerful ideas in all of science. Here it is in plain English, with no numbers at all. Every single object in the universe, every star, every planet, every rock, every person, every dust particle, pulls on every other object with a gravitational attraction. The more massive the objects are, the stronger that pull. And the farther apart they are, the weaker it gets. Move them twice as far apart, and the force drops to 1/4 of what it was. Move them 3 times as far apart, and it drops to 1/9. The force fades with distance in a very specific, very predictable way. That is it. That is the core of Newton's universal law of gravitation. And from that one elegant idea flowed consequences so vast that they reshaped civilization. Think about what it meant that gravity was universal. Before Newton, scholars thought the planets moved in their perfect circles in the heavens for essentially mystical or divine reasons. The heavens were a realm apart from the earthly world of mud and apples and falling things. Newton collapsed that distinction entirely. The moon is not moving in its orbit because it is a heavenly body following divine rules. It is falling. Right now, as you read this, the moon is falling toward the earth. It just keeps missing. Because the moon is also moving sideways, and the earth is round, and so by the time the moon has fallen a little bit closer, the Earth has curved away beneath it. The moon falls and falls and falls, and the Earth keeps curving away, and the result is a stable orbit, an eternal free fall around a curved world. That image, the moon perpetually falling and perpetually missing, is one of the most beautiful ideas in the history of human thought, and Newton gave it to us. The practical consequences were even more astonishing. Astronomers of Newton's time had noticed that a particular comet appeared in the sky every so often and then disappeared again. Using Newton's gravity, a man named Edmund Halley calculated that the comets seen in 1682 and in 1682 and in earlier decades were all the same comet, swinging around the sun on a huge elliptical path and returning to Earth's neighborhood every 75 or 76 years. He predicted it would return in 1758. Halley died before he could see it, but the comet arrived right on schedule. We still call it Halley's Comet today. And then there was the discovery of Neptune, which remains one of the most dramatic demonstrations of scientific power in history. Astronomers in the early 1800s had been carefully tracking the planet Uranus, and they noticed something troubling. Uranus was not quite where Newton's equations said it should be. It was drifting slightly off course, as if something were tugging it gently in a direction no one had accounted for. Two mathematicians working independently, one in England and one in France, did the extraordinary thing of calculating where an unknown planet would have to be in order to cause exactly that disturbance. They worked purely from Newton's equations. They predicted a position in the sky. Astronomers pointed a telescope there, and on the very first night they found Neptune sitting almost exactly where the math said it would be. Newton's gravity had literally discovered a planet through pure mathematics before any human eye had ever seen it. The power of that is hard to overstate. Science was not just describing the world, it was predicting things that had never been seen. And then there were the Apollo missions. In July of 1969, 3 men flew to the moon in a small metal capsule. The calculations that guided that journey, the precise burn of engines at precisely the right moments, the careful arcing path through space, those calculations were done using Newton's equations, essentially the same mathematics Newton had derived while hiding from a plague in his family farmhouse 3 centuries earlier. The man who sat under that apple tree never could have imagined that his equations would one day carry human beings to another world. But they did, and they worked. So why do we say Newton was wrong, or at least incomplete? Here is where it gets interesting. Newton's gravity has a feature built into it that, once you notice it, is deeply troubling. In Newton's model, gravity acts instantaneously. Right now, this very second, you are being pulled by the gravity of the Sun, of Jupiter, of every star in the Milky Way, of every galaxy in the observable universe. And in Newton's framework, if something happened to the Sun right now, if it somehow vanished in this instant, you would feel the gravitational change at this same instant. Not 8 minutes from now, not a second later, right now. The news would travel from the Sun to the Earth in literally 0 time. But by the early 20th century, something was well established in physics that made this completely impossible. Nothing in the universe can travel faster than light. That is not just a rule of thumb or a handy approximation. It appears to be a fundamental law of reality. Information cannot travel faster than light. Cause cannot precede effect. The universe is built in such a way that the past cannot communicate with the future instantaneously across space. And if that is true, Newton's gravity cannot be right. It cannot be the full story, because Newton's gravity involves the whole universe knowing about changes happening everywhere else at the exact same instant, which is another way of saying Newton's gravity requires information to travel infinitely fast, and that appears to violate one of the deepest laws of nature. There was also Mercury. Mercury is the innermost planet in our solar system, the one closest to the Sun. And for most of the 1800s, astronomers had been carefully measuring Mercury's orbit and finding something odd. Mercury does not orbit the Sun in a perfect ellipse. Its orbit precesses, which means the whole orbital path slowly rotates over time, like a pinwheel spinning very, very slowly. This precession was mostly explained by the gravitational tugs of the other planets, but not entirely. There was a tiny remainder, a small but undeniable wobble in Mercury's path that nobody could account for using Newton's gravity no matter how carefully they tried. For over 200 years, this was an open wound in Newtonian physics. Various explanations were proposed. Maybe there was another undiscovered planet even closer to the Sun, pulling on Mercury. They even gave it a name, Vulcan. Astronomers searched for it. They never found it, because it does not exist. The answer lay not in adding another planet, but in replacing Newton's gravity with something deeper. Here is the beautiful thing. Those two problems, the impossibility of instantaneous gravity and the unexplained wobble of Mercury, turn out to be connected. They are both symptoms of the same deeper issue. Newton's gravity is an approximation, a breathtakingly accurate approximation for most everyday situations, but still an approximation. There is a deeper theory underneath it, and that deeper theory would be built not by adding to Newton's equations, but by questioning the very concepts of space and time on which Newton's equations rested. That deeper theory came from a man who, when he first had the key idea, was working 6 days a week as a junior clerk in the Swiss patent office, evaluating other people's inventions for a modest salary. He would spend his lunch breaks and evenings thinking about physics, filling notebooks with ideas that no journal yet wanted to publish. His name, of course, was Albert Einstein, and the story of what he did is one of the most remarkable intellectual achievements in human history. Before we step into Einstein's world, pause for just a moment and appreciate where we are. We have seen that Newton gave us a set of rules so powerful they guided moon missions and discovered new planets, and yet those same rules contain two quiet, nagging problems that pointed towards something deeper. That is the rhythm of science, really. Every great answer contains within it the seeds of the next great question. Newton's triumph contained the seeds of Einstein's revolution. And as we will see, Einstein's triumph contains the seeds of the revolution that physics is going through right now, today, in the 21st century. That is where we are headed. But first, we need to meet Einstein at the moment of his great insight, because it is one of the most human and relatable moments in the history of scientific genius. Gravity isn't a force at all. It's the shape of space itself. The year is 1907. Albert Einstein is 28 years old. He is sitting in his chair at the patent office in Bern, Switzerland, reviewing someone else's invention, and his mind drifts. It drifts, as it often did, toward big questions, and he has what he will later describe as the happiest thought of his life. He imagines a man falling off a roof. Now, you might think that is not a very happy thought, but Einstein was not worried about the man's well-being. He was excited about something the man would experience on the way down, because Einstein realized, with sudden and electric clarity, that a person in free fall feels no weight at all. If you were to fall from a great height, in that terrifying tumbling moment, you would feel weightless, completely weightless. Your stomach would float up the same way it does in an elevator that drops suddenly, except the feeling would not stop. You would be floating inside yourself, even as the ground rushed toward you. Astronauts in the International Space Station feel exactly this sensation. They are not in a place with no gravity. Earth's gravity still reaches them perfectly well. They feel weightless because they are in constant free fall, falling around the Earth so fast that they keep missing it. Einstein stared at this idea. He turned it over in his mind, and he noticed something extraordinary. If a person in free fall cannot feel gravity at all, if the experience of falling is indistinguishable from the experience of floating in empty space with no gravity anywhere nearby, then what does that tell us about what gravity actually is? Let us try a little thought experiment together, because it is the same one Einstein tried. Imagine you wake up inside a completely closed box. No windows, no outside information. The box could be anywhere, and you feel yourself pressed to the floor. You feel your normal weight. Now here's the question Einstein asked: are you on the surface of the Earth, being pulled down by gravity? Or are you in a rocket ship somewhere out in deep space, being accelerated upward by the engine? Is the floor pressing up against you because of gravity from below, or because of acceleration from below? The astonishing answer is, you cannot tell. Not from inside the box. No experiment you could do inside that sealed box, no measurement you could take, would allow you to distinguish between standing in a gravitational field and being accelerated in the opposite direction. They feel identical. They produce identical effects on every object inside the box. They are, as far as any measurement can reveal, the same thing. Einstein called this the equivalence principle. And from this one observation, this single beautiful insight, he spent the next 8 years building an entirely new theory of gravity. 8 years of the hardest mathematics he had ever done. Mathematics so difficult he had to ask a friend to teach him a whole new branch of it. A kind of geometry developed to describe curved surfaces. Why curved surfaces? Because Einstein realized that if gravity and acceleration are truly equivalent, then gravity must be explained by something structural. Something about the shape of the environment. Not a force reaching across space, pulling things, but a curvature, a bend, a warp in the very fabric of space and time themselves. Mass does not reach out and grab things. Mass reshapes the space and time around it, and other objects, moving through that reshaped space and time, follow the natural paths that the curvature provides. Here is the image that most people reach for when explaining this, and it is a good one even though it is imperfect. Imagine a large bed sheet held taut at the corners, stretched out flat and smooth. That is flat space, space with no mass nearby. Now place a heavy bowling ball in the center of the sheet. The sheet sags and curves downward around the ball. Now roll a marble gently across the sheet. It does not travel in a straight line past the bowling ball. It curves toward it, following the contour of the sheet. It might even spiral around the bowling ball if you give it the right speed. It looks exactly as if the bowling ball were pulling the marble toward it. But there is no pull. There is no force between them. There is only the shape of the surface they are both moving through. The bowling ball warped the surface, and the marble followed the warped surface. That is what Einstein says gravity is. Now, the analogy has its limits. The real thing is not a two-dimensional sheet, but a four-dimensional space-time, which our brains cannot really visualize directly. And crucially, in the real universe, it is not just space that bends. Time bends too. Time actually runs slower, closer to a massive object. If you lived at sea level your whole life and had a twin who lived on a mountaintop, your twin's clock would run ever so slightly faster than yours because they are a little farther from Earth's center of mass, experiencing slightly less curvature of time. This sounds like science fiction. It is not. We measure it. Every single day, the GPS satellites that your phone uses to navigate are running their clocks slightly differently than clocks on the ground because they are high above Earth, where space-time curves differently. The engineers who designed GPS had to account for this effect precisely. If they had ignored it and used Newton's gravity instead of Einstein's, Your GPS would drift by several miles of error every single day. The reason your navigation app works accurately is that we built Einstein's corrections into it. Einstein's warped time is not an abstract theoretical curiosity. It is baked into the technology in your pocket. Now, here is where the story gets particularly satisfying, and we return to something we mentioned earlier. Remember Mercury, the planet with the unexplained orbital wobble that had bothered astronomers for 200 years? The wobble that Newton's gravity, no matter how carefully applied, could not account for? When Einstein finished his general theory of relativity in November of 1915 and applied it to the solar system, he calculated Mercury's orbit using his new equations. He was not trying to fix the Mercury problem specifically. He was simply applying his new theory to see what it predicted, and when he worked out the result, the correct wobble came out automatically, perfectly. Without any adjustments, without any fudging, without any free parameters to fiddle with, the number matched the observations exactly. Einstein later said that when he saw this result come out of his equations, he had heart palpitations. He felt something almost like being outside of himself. He had been working on his theory for 8 years, and this calculation, in a single afternoon, confirmed not only that his theory was right, but that it was the right kind of right, the kind where nature itself validates your reasoning. The wobble of Mercury was not a flaw in Newton's theory to be patched. It was a message from Mercury. It was the solar system's way of saying, there is something deeper here. And Einstein received that message and answered it. The world received Einstein's answer in a dramatic fashion in 1919. Einstein's theory made a prediction that seemed testable. Because mass curves space and light travels through space, the path of light should be bent as it passes near a massive object. The sun, being the most massive object we can easily see in the sky, should deflect the light of stars passing near it. But of course, you normally cannot see stars near the sun because the sun is too bright. Unless, that is, the moon passes in front of the sun and blocks its light. During a total solar eclipse, a British astronomer named Arthur Eddington organized 2 expeditions to observe the solar eclipse of May 1919, one to the coast of West Africa and one to Brazil. The eclipse happened. The sky went dark in the middle of the day. Eddington photographed the stars visible near the edge of the eclipsed sun, and when he measured their positions and compared them to where those stars appear when the sun is not nearby, the stars were shifted. They appeared in slightly different positions because the sun's gravity had bent the light from them as it passed close by. The shift was tiny, but it matched Einstein's prediction almost perfectly, and it did not match Newton's prediction at all. Newton's older, simpler theory had predicted some bending of light, but only about half as much as Einstein's theory. The observations matched Einstein. The news made the front pages of newspapers around the world. The headline in the London Times read, "Revolution in Science. New theory of the universe. Newton's ideas overthrown." And overnight, Albert Einstein became the most famous scientist in the world, a fame he would carry, somewhat uncomfortably, for the rest of his life. So here is where we stand at the end of Einstein's great contribution. Gravity is not a force pulling things toward massive objects. Gravity is the curvature of space-time caused by the presence of mass and energy. Objects do not fall toward the Earth because the Earth is grabbing them. They fall because the Earth's mass has bent the geometry of the space around it, and falling objects are simply following the straightest possible path through that bent geometry. That path curves downward, and so they curve downward too. This is a profound and beautiful picture, and it is, as far as any experiment has ever been able to show, correct. Every test we have run in 100 years of trying has confirmed Einstein's theory to extraordinary precision, but here is the thing. And this is the thing that will drive the rest of our journey together today. Einstein's theory tells us what gravity does. It tells us how mass curves space-time. It gives us the equation that connects mass to curvature, but it does not tell us what space-time is. It does not explain what it means for space-time to curve at the quantum level, at the level of the very smallest things. And when we try to push Einstein's theory to its ultimate extremes, when we try to apply it to the universe at the smallest possible scales, something goes terribly wrong. It breaks. Einstein's beautiful theory breaks, and that is where the real mystery begins. The two greatest theories in all of science completely contradict each other. To understand why Einstein's theory breaks down, we first need to understand the other great revolution of 20th century physics. Because while Einstein was rethinking gravity and the large-scale structure of the universe, a completely different group of scientists was rethinking the small-scale structure of matter. And the theory they built, quantum mechanics, is arguably the most successful scientific theory ever created by human beings. Let me tell you what quantum mechanics is about, in plain terms, without the mathematics and without the philosophy debates that tend to distract from the core ideas. At the very smallest scales, nature behaves in ways that have no parallel in everyday experience. Things are not at one place at one time. They exist in clouds of probability. A particle is not here or there. It is in a kind of both here and there superposition until something interacts with it and forces it to choose. Energy does not flow in smooth, continuous streams. It comes in tiny, discrete packets called quanta, like the individual steps of a staircase rather than a smooth ramp. And particles do not interact with each other through invisible forces reaching across space. They interact by exchanging other particles. Force is carried by particles. That last point is the crucial one for our story today. In quantum mechanics, every fundamental force is carried by what physicists call a force-carrying particle or a messenger particle. It is as if, when two particles want to push or pull on each other, they cannot simply reach out and do it directly. They have to throw something to each other. And that something is a particle, the force of electromagnetism, the force that controls all chemistry and makes lights shine and magnets stick to your refrigerator. That force is carried by the photon, the particle of light. Every time an electron in an atom does something, every time electricity flows through a wire, what is happening at the quantum level is an exchange of photons. When two charged particles repel each other, they are throwing photons back and forth. The strong nuclear force, the force that holds the nucleus of an atom together, is carried by particles called gluons. The particles in the nucleus are constantly exchanging gluons, and those exchanges are what keep the nucleus from flying apart, despite the fact that all its protons are positively charged and should be repelling each other fiercely. The weak nuclear force, which is responsible for a certain kind of radioactive decay, is carried by three particles called the W boson, the W- boson, and the Z boson. So we have three fundamental forces, and they each have their messenger particles. The theory that describes all of this, that unifies the quantum descriptions of all three of these forces, is called the Standard Model of Particle Physics. It is one of the great intellectual achievements of the 20th century, and it works astonishingly well. In some of its predictions, it has been confirmed to an accuracy of 1 part in a trillion. That is like predicting the distance from New York to Los Angeles to within the width of a human hair. Now, what about gravity? Gravity is missing from this picture entirely. The Standard Model, the great unified quantum theory of three fundamental forces, simply does not contain gravity. It was not left out by accident or laziness. Physicists have been trying for nearly 100 years to incorporate gravity into the quantum framework, and every attempt has led to the same result: nonsense, mathematical nonsense. When you try to describe gravity using the same tools that work beautifully for the other three forces, the equations produce infinities, not large numbers, literal infinities, which means the equations are telling you that the probability of something happening is infinite, or that a particle has infinite energy, or that some physical quantity is infinitely large. Infinite answers are meaningless. They are the equation's way of saying, you are asking the wrong question, or you are using the wrong framework. Let us use a simple image to appreciate how strange this situation is. Imagine you are a map maker. You have been given the job of creating a complete map of a city. You have two maps already, both of them extraordinarily detailed and accurate in their own domain. One map shows the large-scale layout of the city perfectly, the highways and neighborhoods and parks and rivers, every large feature accurate to the inch. The other map shows the interiors of buildings perfectly, every room, every staircase, every doorway, down to the millimeter. Both maps are the best possible maps of their respective domains. No better map of the neighborhoods exists. No better map of the building interiors exists. But when you try to combine them into one unified master map, they contradict each other. Roads appear to run through the walls of buildings. Staircases come out on the wrong sides of structures. The two maps, each perfect in itself, are fundamentally incompatible at their boundaries. You cannot simply paste them together. You need a new kind of map, built on different principles, that can reconcile what both maps are accurately showing. That is the situation in physics today. General relativity is the perfect map of large things. Quantum mechanics is the perfect map of small things. And they are incompatible. We need a new framework, a theory of quantum gravity that can reconcile them. And we do not have it yet. Now you might be wondering, does this really matter? If general relativity works for big things and quantum mechanics works for small things, and they each work perfectly in their own domain, why not just use each one where it applies and not worry about combining them? The answer is that there are places in the universe where you cannot separate the two. Places where things are simultaneously incredibly massive and incredibly small, and where both theories must apply at the same time. And in those places, our physics simply stops working. We hit a wall. The most vivid example is a black hole. A black hole forms when a massive star has burned through all its fuel, and there is nothing left to hold it up against its own gravity. The outer layers explode in a supernova. The core collapses, and it keeps collapsing, past the point where normal matter can support itself, past the density of an atomic nucleus, past any state of matter we know how to describe. It collapses to what the math calls a singularity, a single point of infinite density at the center of a black hole, a point where general relativity's equations produce those same frightening infinities. But wait, a point. The smallest possible thing. Infinite density packed into zero volume. That sounds like a quantum problem. That sounds like something that should be described by the laws of the very small. But general relativity, our theory of gravity and large things, is breaking down right there, and quantum mechanics is not equipped to handle the gravitational collapse of an entire star. Both theories reach their limit at the center of a black hole. Both of them break. And the truth of what is actually happening there in those extreme conditions is completely hidden from us. We do not know. We cannot calculate. Our best theories, the two most accurate theories we have ever built, both fail us at the exact moment we need them most. There is also the very beginning of the universe. In the earliest fraction of a second after the Big Bang, the entire observable universe was compressed into a region smaller than a proton, a region that was simultaneously unimaginably massive and unimaginably tiny, a situation that absolutely requires both general relativity and quantum mechanics to describe accurately. And again, when we try to apply both theories at once, the math explodes into nonsense. We are essentially blind to the first instant of creation. We have a beautiful story of the universe from a fraction of a second after the Big Bang onward, but that first tiny sliver of time is hidden behind a mathematical wall built from the incompatibility of our two greatest theories. There is one more piece to this puzzle before we move on, and it is perhaps the most tantalizing. In quantum mechanics, since every force is carried by particles, gravity too should be carried by a particle if gravity is to fit into the quantum picture. Physicists have given this hypothetical particle a name. They call it the graviton. The graviton has never been detected. We have never seen one. We have never measured one indirectly. But based on everything we know about how quantum mechanics works, if gravity is quantum mechanical in nature, then gravitons should exist. They should be massless, like photons. They should travel at the speed of light. They should carry gravity the way photons carry light. And finding one, or even finding convincing indirect evidence that they exist, would be one of the greatest discoveries in the history of science. So why have we not found them? Why, after decades of searching and building and experimenting, do we still have no graviton? That story is its own mystery, and it is where we go next. Finding gravity's particles should be simple. It turns out to be almost cosmically impossible. Let us start with a thought that seems simple, but leads somewhere very dark. If gravity is quantum mechanical, and if every quantum mechanical force is carried by a particle, then finding the graviton should be just a matter of building a good enough detector and waiting for one to show up. That is how we found the other force-carrying particles. We built bigger and more powerful accelerators and colliders, smashed things together with more energy, and the particles revealed themselves. The W and Z bosons were predicted theoretically and then found in experiments. The Higgs boson was predicted in 1964, and finally detected in 2012 at the Large Hadron Collider in Switzerland. The pattern is consistent. Predict the particle. Build a machine powerful enough to find it. Find it. So let us build a graviton detector. How big would it need to be? Here is where things take a breathtaking turn. Gravity is the weakest force in nature, and I do not mean slightly weaker or a bit weaker. I mean incomprehensibly, almost insultingly weaker than the other forces. Let me try to give you a sense of just how weak it is. Pick up a small metal paperclip, place it on a table. Now take a small refrigerator magnet, the kind people put on their fridge to hold up grocery lists, and hold it above the paperclip. The magnet will lift the paperclip right off the table. It will overcome the gravitational pull of the entire planet Earth and lift that paperclip against it. A little souvenir magnet, the kind you might buy at a tourist shop, can outmuscle the entire planet. Now think about that. The Earth is 6,000 quadrillion pounds of mass, all of it pulling down on that paperclip, and a thin strip of refrigerator magnet beats it. Electromagnetism is that much stronger than gravity, and the strong nuclear force that holds atomic nuclei together is roughly 100 times stronger still. Why is gravity so weak? Nobody knows. That weakness is itself one of the deepest unsolved mysteries in physics. Physicists call it the hierarchy problem. But the consequence of that weakness for our story is this. Individual gravitons, the hypothetical carrier particles of gravity, would interact with matter so weakly that detecting even one of them would require a detector of almost incomprehensible size. Physicists have actually done the calculation. They asked, how big would a particle detector need to be in order to have a reasonable chance of detecting even a single graviton? And the answer they arrived at was a detector roughly the size of Jupiter, a sphere of matter as large as the largest planet in our solar system operating as a graviton detector. And even at that size, you might have to wait longer than the current age of the universe, more than 13 billion years, to register a single hit. Let that settle for a moment. A detector the size of Jupiter, waiting longer than the history of the universe for one particle. This is not a failure of our technology. This is not a problem that will be solved by making a better instrument in the next decade or building a slightly larger particle accelerator. This is a fundamental consequence of how weakly gravity interacts with matter. Detecting an individual graviton may be literally impossible, not just difficult, but actually prevented by the laws of physics as we understand them. Some physicists, when confronted with this problem, have said something even more disturbing. They have suggested that the graviton may not exist at all, that gravity may be fundamentally different from the other three forces, that gravity may be something that simply cannot be quantized, cannot be made into a quantum theory, and that our whole approach of looking for a messenger particle for gravity is based on a wrong assumption. That is a radical idea. If it is true, it would mean that the standard approach of quantum field theory, which has worked brilliantly for 3 of the 4 forces, simply does not apply to gravity. It would mean that gravity is not just quantitatively different from other forces, but qualitatively different. Different in kind, not just in degree. And it would mean that building a theory of quantum gravity cannot be done by simply extending the tools that worked for the other forces. We would need something genuinely new, something that maybe has not been invented yet. But here is where a ray of light enters this dark picture. Even if we cannot detect individual gravitons, we can detect gravity in some very dramatic and very beautiful ways. And in the 21st century, we have done exactly that. In September of 2015, something happened that made grown physicists cry tears of joy in their offices and laboratories. A detector called LIGO, the Laser Interferometer Gravitational Wave Observatory, detected a ripple in spacetime that had been traveling for more than 1 billion years. It was produced by 2 black holes, each roughly 30 times the mass of our Sun, spiraling toward each other and finally colliding and merging into one. In the last fraction of a second of that collision, those 2 black holes released more energy than all the stars in the observable universe combined. Most of that energy went into a burst of gravitational waves, ripples in the fabric of space-time itself, that then spread outward in all directions at the speed of light. 1 billion years later, that ripple passed through the Earth. It compressed and stretched space-time as it did. The compression and stretching was a fraction of the size of a proton. Actually, not even that. It was 1,000th of the width of a proton. LIGO measured it. LIGO had been built specifically for this purpose, with laser beams bouncing back and forth along tunnels several miles long, sensitive enough to detect a change in length smaller than any measurement ever made in human history. And it worked. The signal was clear, unmistakable, and perfectly matched the predictions of Einstein's general relativity for what 2 merging black holes should produce. This was the most sensitive measurement in the history of human science, and it confirmed that space-time really does ripple. Gravity really does travel as waves. And those waves really do move at exactly the speed of light, not instantaneously the way Newton assumed. Now, here is the important distinction. Gravitational waves are not gravitons. They are related, but separate. Gravitational waves are classical ripples in spacetime, like waves on the surface of a pond. They follow the rules of Einstein's general relativity, which is not a quantum theory. Detecting gravitational waves was an extraordinary triumph. It confirmed Einstein's predictions beautifully. But it did not tell us whether gravitons exist. It did not tell us whether gravity has a quantum structure. Finding a gravitational wave is like finding a wave in the ocean. It does not tell you what the individual water molecules are made of. To find the graviton, if it exists, we would need to detect the individual quantum grains of a gravitational wave, the individual water molecules, to continue the analogy. And that, as we have just seen, may be beyond our reach using any technology we can imagine today. So here is where the story stands at the end of this hunt. We know gravity exists. We can measure it with extraordinary precision. We can detect it rippling through spacetime at the speed of light. We have seen it bend light from stars and shape the orbits of planets and hold galaxies together. But its quantum nature, its inner machinery, its deepest structure, remains hidden from us. And so the best minds in theoretical physics have taken a different approach. Rather than waiting for an experiment that may be impossible, they have turned inward. They have retreated to paper and blackboards and computers, and they have begun building theories from pure mathematics, from pure logic, from first principles, asking, if we had to build a quantum theory of gravity from scratch, using everything we know about quantum mechanics and general relativity and the structure of the universe, what would it look like? The answers they have come up with are, without exception, the strangest ideas ever seriously entertained by the human mind. It is time to look at them. What if space isn't fundamental? What if gravity is made of information? We are now entering the frontier. Everything we have talked about up to this point, Newton's laws, Einstein's curved space-time, quantum mechanics, the Standard Model, gravitational waves, even the frustrating impossibility of detecting the graviton, all of that is established science. It is either confirmed experimentally, or it is the direct consequence of confirmed experimental results. What comes next is different. What comes next is the bleeding edge of theoretical physics, the ideas that physicists are working on right now, debating right now, arguing about in journals and at conferences and late at night over bad coffee in university corridors. Some of these ideas are decades old and still have not been confirmed. Some are newer and have not yet even been fully developed. None of them has been proven. All of them are serious science, taken seriously by serious people. What they all share is a willingness to question things that most of us take completely for granted. Things like the existence of space as a real thing, the continuity of time, the separateness of distant objects, the very concept of inside and outside. These theories ask whether the furniture of reality that we have always assumed to be fixed and fundamental might instead be emergent, built up from something else, something deeper, something we have not yet directly seen. The first wild idea, string theory. Let us begin with the most famous of these theories, and perhaps the most controversial. It is called string theory, and it has been one of the central projects of theoretical physics for the past 50 years. String theory begins with a simple but radical question. What if the fundamental constituents of the universe are not point-like particles at all? In the Standard Model, electrons, quarks, and all the other particles are treated as mathematical points. They have no internal structure, no size, no extent. They are infinitely small. And this leads to some of those ugly infinities we mentioned earlier, because when you try to calculate what happens when two point-like particles interact at the same place at the same time, the math tends to blow up. What if, instead of points, the fundamental things are tiny, vibrating loops of energy? Strings. Not strings made of any material, but one-dimensional strands of pure energy, vibrating in different patterns the way a guitar string can vibrate at different frequencies to produce different notes. And just as a guitar string produces different musical tones depending on how it vibrates, a fundamental string produces different particles depending on its vibrational mode. An electron is a string vibrating one way. A quark is a string vibrating another way. A photon is a string vibrating in yet another pattern. And here is the crucial part for our story. When physicists worked out the mathematics of string theory fully, they found that one particular vibrational mode of the string corresponds to a massless spin-2 particle that travels at the speed of light. You might not recognize those technical terms immediately, but here is what they mean. Those are exactly the predicted properties of the graviton. String theory, without anyone designing it to do so, automatically produces a particle that looks exactly like the graviton should look. This was seen as a profound hint. Gravity, in string theory, is not something you have to add to the theory as an afterthought. It falls out of the mathematics naturally. The graviton is just one more vibrating string, like every other particle. This was the first time in the history of physics that a theory naturally incorporated all four fundamental forces, including gravity, within a single consistent framework. But the price tag for this elegance is extraordinary. For string theory's mathematics to be consistent, for the equations to work without producing contradictions, the universe must have more than the 4 dimensions we experience. Specifically, it must have 10 or 11 dimensions in total. The familiar 4 we know, 3 dimensions of space plus 1 of time, plus 6 or 7 additional spatial dimensions that are curled up on themselves so tightly that they are invisible to any probe we have. Picture an ordinary garden hose lying on the ground, seen from a great distance. From far away, the hose looks like a one-dimensional line. It has length but no apparent width. But if you get close enough, you see that the hose actually has a second dimension. It is a tube, and you can travel around its circumference as well as along its length. The extra dimensions of string theory might be something like this. At the scales of everyday life, and even at the scales probed by particle accelerators, they are simply too small to detect, but they are there. The deep problem with string theory, the reason it remains controversial after 50 years of extraordinary mathematical development, is that it has so far produced no specific experimental predictions that we can test. It describes a vast landscape of possible universes, many of them with different properties, and has not yet told us why our universe looks the way it does rather than some other way from that landscape. A theory that can explain everything in principle but predicts nothing specific in practice is, from a scientific standpoint, in a very uncomfortable position. Many physicists defend string theory as a work in progress, a mathematical framework of profound power that has not yet matured to the point of making testable predictions, but that contains deep truths nonetheless. Others argue more critically that after 50 years, this defense is wearing thin. The debate continues, and it is one of the most vigorous and sometimes heated debates in modern physics. The second wild idea: loop quantum gravity. If string theory modifies what matter is, our second major contender modifies something more radical. It modifies what space itself is. Loop quantum gravity starts from a question that sounds almost philosophical. We take it for granted that space is smooth and continuous, that between any 2 points in space, no matter how close together, there are always more points. Space, in our everyday intuition, is like a perfectly smooth piece of glass. You can zoom in as far as you like and it just stays smooth. But what if that is not true? What if, at some unimaginably small scale, space has a grain structure? What if, just as matter is made of atoms and light is made of photons, space itself is made of tiny, discrete chunks, a kind of quantum foam, a pixelated reality at the most fundamental level? The scale at which this would happen is called the Planck length, named after the physicist Max Planck, who first identified the significance of this scale. The Planck length is roughly 10 to the power of negative 35 meters. That is a decimal point followed by 34 zeros and then a 1. It is smaller than a proton by about the same factor that a proton is smaller than the observable universe. It is, in any practical sense, inconceivably small. We have never probed anything close to this scale with any experiment. Our best particle accelerators probe scales that are still a trillion times larger than the Planck length. But here's the theoretical argument that loop quantum gravity makes. When you try to apply the mathematics of general relativity and quantum mechanics together at the Planck scale, The structure of space-time itself becomes quantum mechanical. It fluctuates. It is uncertain. It comes in discrete units. Space, at the deepest level, is not a smooth, continuous fabric. It is a network, a foam, a web of discrete chunks of geometry, each one the smallest possible unit of space. In this picture, what we experience as smooth space is an approximation that emerges when you have enormously many of these fundamental units packed together, just as what you experience as a smooth tabletop is an approximation that emerges from trillions of atoms packed closely together. Zoom in far enough on the tabletop and it becomes grainy and bumpy. Zoom in far enough on space and it would too. And gravity, in loop quantum gravity, is simply the way these fundamental units of space interact with each other. When mass is present, it changes the relationships and connections between the units. The pattern of connections becomes what we experience as curved spacetime. The graviton, if it exists in this framework, would be a vibration or a wave in this network of spatial units, rippling through the quantum foam. Loop quantum gravity has an appealing directness. It takes general relativity seriously as the correct description of gravity, and simply asks what happens when you apply quantum mechanics to the geometry of space itself. It does not require extra dimensions. It does not require strings. It modifies our understanding of space at the deepest level, but only at scales so small that we have never directly examined them. Its challenges are different from string theories. The mathematics is extraordinarily complex. Making calculations in loop quantum gravity is hard enough that testing many of its predictions is currently beyond our reach. But some predictions may be testable with future gravitational wave observatories or gamma-ray telescopes by looking for tiny deviations from what Einstein's smooth spacetime would predict at very high energies. If space has a grain structure, high-energy light should travel very slightly differently than low-energy light. Some experiments are beginning to look for exactly this effect. The third wild idea: emergent gravity. Now we come to the idea that some physicists find the most compelling and others find the most troubling. It is called emergent gravity, and its most striking version was proposed relatively recently by the Dutch physicist Erik Verlinde. What if gravity is not a fundamental force at all? Not just in the sense of needing a deeper quantum description, but in the sense of not being a real force in any deep sense. What if gravity is emergent, meaning it arises from the collective behavior of something even more fundamental, the way that temperature emerges from the motion of countless atoms? Let us think about temperature for a moment. When you feel warmth, you are feeling the effect of trillions of atoms moving rapidly and bumping into your skin. Temperature is a real and measurable thing. It affects the world in enormous ways, but it is not fundamental. There is no temperature particle. Temperature is a statistical concept, a description of the average behavior of a huge number of things. It emerges from the underlying physics without being a separate fundamental ingredient of that physics. Verlinde argues that gravity might be exactly like this, that it emerges from the statistical behavior of some more fundamental level of reality, in the same way that temperature emerges from atomic motion. In Verlinde's specific version of this idea, gravity emerges from something called entropy, which is roughly a measure of how many ways a system can be arranged. Entropy tends to increase over time, because there are always more disordered arrangements of things than ordered ones, and random processes tend to find the more common arrangements. Verlinde argues that this tendency, this universal drift toward higher entropy, is what we experience as the gravitational attraction between masses. This might sound impossibly abstract, but consider what it would mean if it were true. It would mean that gravity is not in the same category as electromagnetism or the strong nuclear force. It is not a force in the fundamental sense at all. It is an effective description that emerges from deeper physics, the way pressure is an effective description that emerges from the collective impact of gas molecules. There is no pressure particle, there is no temperature particle, and perhaps there is no graviton. Perhaps the whole graviton search is looking for something that does not exist, because gravity is not that kind of thing. Verlinde's ideas are controversial. Many physicists are skeptical, but some find them deeply appealing, particularly because emergent gravity might naturally explain some things that are otherwise puzzling, like why gravity is so much weaker than the other forces. If gravity is emergent rather than fundamental, it would naturally be softer, more diffuse, a pale shadow of whatever is actually happening at the deeper level. Its weakness would not be a mystery to be explained, but a natural consequence of its emergent character. The fourth wild idea, the holographic universe and gravity from entanglement. And now we come to the strangest and, to many physicists working today, the most exciting idea of all. It is the idea that gravity might be made of quantum information, that the fabric of space-time might be literally stitched together by quantum entanglement, and that the universe might be, in some profound mathematical sense, a hologram. Let us build up to this gently. Quantum entanglement is one of those features of quantum mechanics that Einstein famously called spooky action at a distance. When two particles interact in the right way, they can become entangled. This means their properties become correlated in a way that persists even when the particles are separated by enormous distances. When you measure one of them and find it has a particular property, the other one instantly has the corresponding property, no matter how far away it is. This does not allow information to travel faster than light. The correlation is real, but you cannot use it to send a message. But it is genuinely strange. The two particles share a kind of connection that transcends the space between them. They are correlated in a way that cannot be explained by any information they exchanged before they were separated. For most of the 20th century, entanglement was seen as a weird quantum curiosity, philosophically puzzling, but practically a bit beside the point when it came to the big questions of gravity and space-time. Then a remarkable thing happened. In the 1990s, a physicist named Juan Maldacena discovered a mathematical correspondence between a theory of gravity in a certain kind of curved space and a quantum field theory without gravity living on the boundary of that space. The two theories, one with gravity in a higher dimensional space and one without gravity on a lower dimensional boundary, turned out to be mathematically equivalent. What happened in one corresponded precisely to what happened in the other. The information was the same, just encoded differently. This is the holographic principle. The idea that a volume of space with gravity inside it can be completely described by information on its boundary, just as a three-dimensional hologram can be encoded on a two-dimensional surface. The inside and the outside are not separate realities. They are two different mathematical languages for describing the same reality. The implications are dizzying. If the holographic principle is correct, then in some sense our three-dimensional experience of space may be a kind of projection of a two-dimensional reality. The depth of the world, the insideness of things might be emergent. It might be a product of the information structure on a surface, not a fundamental feature of reality. More recently, Maldacena and another physicist named Leonard Susskind pushed this even further with an idea they expressed as a short equation. ER equals EPR. In that equation, ER refers to Einstein-Rosen bridges, which is another name for wormholes, the hypothetical tunnels through space-time that Einstein and Rosen first described mathematically in 1935. And EPR refers to Einstein, Podolsky, and Rosen, the three physicists who first analyzed quantum entanglement in that same year of 1935. What Maldacena and Susskind proposed is that these two things, wormholes and entanglement, are not merely analogous, they are the same thing. Two entangled particles might actually be connected by a tiny wormhole, a microscopic bridge through spacetime. The spooky connection of entanglement would not be action across empty space at all. It would be action through a wormhole, a literal geometric connection between two apparently distant points. And if this is right, then here is the extraordinary conclusion. If entanglement and wormholes are the same thing, and if wormholes are made of spacetime geometry, and if spacetime is what gravity acts on, then the entanglement between particles is literally weaving spacetime together. Spacetime, the arena in which gravity operates, might be built from the quantum entanglement of some more fundamental constituents. Gravity might be the geometry of entanglement. The force that holds the universe together at the largest scales might be woven from the quantum connections between things at the smallest scales. In other words, gravity might be made of information, not in a metaphorical or philosophical sense, in a precise mathematical sense that physicists can calculate and, at least in some simplified settings, verify. This is where physics is today. This is the frontier. It is genuinely strange. It is stranger than anything most people encounter in their daily lives, or even in popular science books. But it is not science fiction. It is the serious, peer-reviewed work of some of the best mathematical minds on the planet. And some of them feel, cautiously and with appropriate scientific humility, that they are getting warm. Let us now turn away from the theoretical for a little while. Let us look at what the universe itself has been showing us, the observational clues that have been accumulating, the evidence that does not fit neatly into our existing theories, and that might be pointing us toward the answer. There is a kind of humility that science at its best always returns to. No matter how beautiful the theory, no matter how elegant the mathematics, the universe is the final judge. If the observations do not match the predictions, the theory is wrong. Full stop. No matter how much you love it, no matter how much time you spend on it, the universe votes last. So let us spend some time with what the universe has actually been telling us. Because mixed in with the confirmations of what we already know are some deeply puzzling signals that point towards something we do not yet understand. Gravitational lensing and the dark matter. Mystery. One of the most striking and beautiful demonstrations of Einstein's gravity is what we call gravitational lensing. Because mass curves spacetime and light follows the curves of spacetime, a massive object can bend the light from objects behind it, acting like a lens made of gravity rather than glass. We see this happening on a grand scale in the universe. When we look at distant galaxy clusters through powerful telescopes like the Hubble Space Telescope or the newer James Webb Space Telescope, we see something extraordinary. The galaxies in the background, billions of light years beyond the cluster, appear distorted. They are stretched into arcs. Some of them appear multiple times, their images smeared around the cluster in rings or partial rings. The cluster is acting as a gravitational lens, bending and focusing and distorting the light from galaxies behind it. But when astronomers measure how much lensing is occurring and try to figure out how much mass would be needed to produce that much bending, they get a shocking answer. The mass needed is far greater than the mass of all the visible matter in the cluster. All the stars, all the gas, all the dust, all the planets, everything we can see or detect directly. It accounts for only about 1/5 of the mass needed to explain the lensing. The other 4/5 is invisible to us. We call it dark matter. And it is not dark the way a cave is dark just because the light has not reached it. It is dark because it does not interact with light at all. It does not emit light, it does not absorb light, it does not reflect light. The only way we know it is through its gravitational effect, which is enormous. Dark matter outweighs ordinary matter in the universe by a ratio of roughly 5-to-1. The stuff we are made of, the atoms and molecules that compose everything we have ever seen or touched or built or eaten or loved, that is a minority ingredient in the universe. Most of the mass of the cosmos is in something we have never directly detected. What is dark matter? Nobody knows. Physicists have proposed many candidates: exotic particles left over from the early universe, particles that only interact through gravity, black holes formed in the early cosmos. Many experiments have searched for dark matter particles directly, looking for the rare occasions when a dark matter particle might bump into an ordinary atom. So far, nothing. The searches continue, increasingly sensitive, increasingly sophisticated. But dark matter remains one of the great open mysteries of physics. And it is relevant to our story because dark matter, whatever it is, interacts with gravity. Its gravitational effect is what revealed its existence. Any complete theory of quantum gravity will need to account for dark matter, either by identifying what dark matter particles are, or by modifying our understanding of gravity in a way that removes the need to invoke dark matter at all. The expanding universe and dark energy. If dark matter is mysterious, what comes next is even more so. In 1998, two independent teams of astronomers were doing what seems like relatively routine observational work. They were measuring the distances and velocities of very distant exploding stars, supernovae, to chart the expansion of the universe. The universe has been expanding since the Big Bang, and everyone assumed that the expansion was slowing down. Gravity, after all, is attractive. All the matter in the universe is pulling on all the other matter. So the expansion should be decelerating over time, gravity gradually applying the brakes. What the astronomers found instead was so unexpected that some of them initially thought they had made an error. The expansion of the universe is not decelerating, it is accelerating. The universe is not just expanding, it is expanding faster and faster. Something is pushing space apart, overcoming the attractive pull of gravity on the largest scales. Something is acting like gravity in reverse, a repulsive force built into the structure of space itself. Physicists gave this something a name: dark energy. And here is a number that should make you pause. Dark energy, this invisible, repulsive something we cannot identify, makes up approximately 68% of the total energy content of the universe. Dark matter makes up roughly 27%. All the ordinary matter, everything made of atoms, every star, every planet, every galaxy we have ever observed, everything in every museum and every library and every ocean on Earth, all of that together makes up less than 5% of the universe. We live in a universe that is 95% mystery. The candidate for dark energy that physicists most often discuss is something called the cosmological constant. It is a number that can be added to Einstein's equations to represent the energy density of empty space itself. Empty space in this picture is not truly empty. It has energy. And that energy, spread across the vast reaches of the cosmos, is enough to push space apart at an accelerating rate. Here is the strange thing. Einstein actually introduced the cosmological constant back in 1917, before the universe's expansion was even known. He added it to his equations for a completely different reason, to try to make his equations describe a static, non-expanding universe, because at the time most scientists assumed the universe was not changing overall. When Edwin Hubble discovered in 1929 that the universe was expanding, Einstein called the cosmological constant his greatest blunder and removed it from his equations. And then in 1998, it came roaring back. The very term Einstein had discarded as a mistake turned out to be needed after all, not to stop the expansion, but to explain its acceleration. The greatest blunder of history's greatest physicist turned out not to be a blunder at all. This is the kind of story that reminds you science is not a straight road. The first image of a black hole. In April of 2019, something remarkable happened. A collaboration of radio telescopes spread across the Earth from Hawaii to Spain to the South Pole, linked together to form an Earth-sized virtual telescope called the Event Horizon Telescope, produced the first actual image of a black hole, specifically of the supermassive black hole sitting at the center of a galaxy called M87, 55 million light-years away. The black hole has a mass 6.5 billion times that of our Sun. The image showed a bright ring of hot glowing gas surrounding a dark central region, the shadow of the event horizon. The event horizon is the boundary around a black hole beyond which nothing, not even light, can escape. The light near the black hole was bent into a precise ring shape by the black hole's intense gravity, just exactly as Einstein's equations predicted it should be. Every detail of that image was consistent with general relativity. The size of the shadow, the shape of the bright ring, the asymmetry caused by the hot gas swirling faster on one side than the other. Einstein's theory passed this extraordinary visual test with full marks. But here is the part of the black hole story that keeps physicists awake at night. What happens at the center? What is actually there? General relativity says that at the center of a black hole, matter has been crushed to infinite density, a singularity, a mathematical point where the curvature of space-time is infinite, where the equations produce those frightening, meaningless infinities we talked about earlier. Now, every time we have seen infinities appear in a physical theory before, they have turned out to be symptoms of an incomplete theory. When infinities appeared in early quantum electrodynamics, the quantum theory of electromagnetism, they signaled that the theory needed to be extended, and the technique of renormalization was developed to handle them. The infinities did not mean the theory was wrong. They meant the theory was incomplete, that it was being pushed beyond its domain of validity. The infinities at the center of a black hole are telling us the same thing. General relativity is being pushed beyond its domain of validity. Something else takes over at the center of a black hole, something we do not yet have a theory for. Quantum gravity. Whatever it is that describes gravity at the quantum level must describe what actually happens in that unimaginably extreme environment. The universe is showing us, right at the center of every black hole, the precise location where we need a new theory. It is almost as if the cosmos has placed a signpost there, pointing directly at the gap in our understanding. We touched on gravitational waves earlier when we discussed LIGO, but let us appreciate them more fully here. Because since that first detection in 2015, LIGO and its partner observatories have detected dozens of gravitational wave events, pairs of black holes merging, pairs of neutron stars colliding, a neutron star and a black hole coming together. Each event sends a chirp of gravitational waves through space-time that tells us in extraordinary detail about the masses, the spins, and the final states of the objects involved. It is like developing a completely new sense. Before gravitational wave astronomy, we could only observe the universe through light, in all its forms from radio waves to gamma rays. But gravitational waves are not light. They pass through everything. They are not blocked by gas clouds or dust. They carry information about events that produce little or no light, like two black holes merging in empty space. We have opened an entirely new window on the universe, a window that lets us hear, in a metaphorical but very real sense, events that were previously completely invisible to us. And as we detect more events with increasing precision, every one of them so far has been consistent with Einstein's general relativity. Not in rough terms, not approximately, but in exquisite detail. Einstein's theory, built purely from mathematics and thought experiments over a century ago, keeps passing test after test after test in the most extreme environments the universe has to offer. And yet, every one of these tests also leaves open the possibility of something deeper underneath. Consistent with general relativity does not mean proven to be exactly general relativity all the way down to the quantum level. The tests we can do with current instruments probe gravity in regimes where quantum effects are negligible. The quantum fingerprints, if they exist, are far too small to see with what we have today. The message from the universe is consistent. Einstein was right about the large-scale behavior of gravity, and we still do not know what gravity is at the deepest level. We have traveled a long way together today. Let us take a quiet moment to look back at the road we have walked. We started in an orchard in 17th century England, where a young man in plague quarantine watched things fall and asked why. We followed Newton's mathematical genius as he unified the heavens and the earth under a single set of rules, rules so powerful they would guide human beings to the moon 3 centuries later. We saw Newton's quiet honesty in admitting that he could describe gravity beautifully but could not explain what it fundamentally was. We then followed Einstein's even deeper journey, from a thought experiment about a falling man to a complete reimagining of the nature of space and time. We saw how Einstein revealed that gravity is not a force but a geometry, that mass bends the fabric of the universe, and that other objects simply follow the curves of that bent fabric. We saw this beautiful theory confirmed by Mercury's orbit, by starlight bending around the sun, by the clocks inside GPS satellites, and by the first image of a black hole. We then confronted the great tension at the heart of modern physics, the incompatibility of Einstein's general relativity and quantum mechanics, the two most powerful and most precisely tested theories in all of science, sitting side by side in complete contradiction with each other. We saw why finding the graviton, gravity's hypothetical quantum messenger particle, may be essentially impossible with any technology we can currently imagine. And we explored the wild frontier theories, string theory's vibrating loops, loop quantum gravity's pixelated space, Verlinde's emergent gravity, and the extraordinary idea that spacetime itself might be woven from quantum entanglement, and that gravity might ultimately be made of information. Now let us be completely honest about where this leaves us. We do not have the answer. There is no moment in this story where a physicist stands up from their desk and shouts that they have figured it out and the puzzle is solved. That moment has not come yet. The question of what gravity is fundamentally made of remains open. Genuinely, seriously, beautifully open. But let us also be honest about what that openness means. Because in science, an open question of this depth and centrality is not a cause for despair. It is a cause for excitement. It means that the most important discovery in physics, perhaps the most important scientific discovery of the century, has not been made yet. It is still out there, waiting, and the people working toward it are alive today. Some of them are young people who have not yet done their greatest work. The person who finally cracks open the quantum nature of gravity might be sitting in a university somewhere right now, perhaps just beginning to ask the right questions. Let us return to the apple one more time. When that apple fell in Newton's orchard, here is what different theories say was actually happening. Newton would say, the Earth is pulling the apple toward it with a force proportional to their masses and inversely proportional to the square of the distance between them. Einstein would say, the apple is following a geodesic, the straightest possible path through the curved space-time created by the Earth's mass. It is not being pulled, it is simply moving freely through a bent geometry. A string theorist would say, the apple and the Earth are exchanging gravitons, which are a specific vibrational mode of fundamental strings in a 10 or 11-dimensional space-time. A loop quantum gravity physicist would say, the apple is moving through a quantum foam of discrete spatial units, and the structure of that foam, shaped by the Earth's mass, guides the apple's trajectory. Eric Verlinde might say, the apple is not responding to a force at all. It is responding to the statistical gradient of entropy in the information field surrounding the Earth. And the most cutting-edge ideas would say, The apple and the Earth are part of an entanglement network, a web of quantum information that defines the geometry of space itself, and the apple falls because the structure of that entanglement network curves in a way that we experience as downward. They cannot all be right. Perhaps none of them is completely right, but each one of them contains something true, or at least something that points toward the truth, and each one is vastly more interesting than the simple wallpaper version, the version where gravity is just the thing that makes stuff fall down. Why does this question matter beyond the pure intellectual pleasure of asking it? Let us think about that honestly. Every time in history that humanity has understood a fundamental force at a deep level, that understanding has transformed civilization in ways nobody predicted. When people first understood electricity at the level of electrons and electromagnetic fields, they built the industrial age, electric motors, generators, radio, telegraph, telephone. When they understood the quantum mechanics of electrons and materials, they built semiconductors, transistors, computers, smartphones, the internet. Every deep understanding of a fundamental force has, within a generation or two, produced technology so transformative that the people who made the discovery could not have imagined it. Understanding gravity at the quantum level would be the deepest understanding of the deepest force we have ever achieved. What would it produce? We genuinely do not know. That is not false modesty. It is honest recognition that the applications of a theory of quantum gravity are as far beyond our current imagination as the internet would have been beyond the imagination of the people who discovered the electron. They did not know they were building toward the internet. They were just following the truth. What we can say is that a complete theory of quantum gravity would give us a complete description of the structure of spacetime at all scales, including the smallest possible scales, the Planck scale, where the quantum nature of space and time becomes apparent. It would tell us what happened in the very first instant after the Big Bang, revealing the deepest origins of everything we see around us. It would tell us what actually happens at the center of a black hole. It would potentially reveal whether the large-scale structure of the universe, the distribution of galaxies, and dark matter and dark energy is explained by a deeper physics we have not yet seen. And perhaps most profoundly, it would answer one of the deepest philosophical questions humanity has ever asked. What is space? What is time? And are these things fundamental features of reality or emergent products of something even more basic? That question, asked by philosophers for thousands of years, turns out to be answerable in principle by physics. And physics is getting closer. There is something quietly moving about the place this question occupies in science. Gravity is the first force we noticed. Children understand that things fall before they learn anything else about physics. It is the force most deeply embedded in our daily experience. It is the force that shaped our planet and our solar system and the galaxies themselves. It is, in a very real sense, the force that made the universe look the way it does, that pulled matter together into stars and planets and you and me. And it is the one force we understand least, at the deepest level. There is a beautiful irony in that. The most familiar thing, the one we have lived with longest and taken most for granted, turns out to be the deepest mystery. The thing that seems most obvious, things fall down, hides the most profound truth. That is not unusual in science. Water is the most familiar substance on Earth, and turns out to have deeply strange properties that physicists are still working to fully explain. Light, which we take completely for granted, turned out to be the door through which Einstein walked to discover relativity. The most ordinary things, when you look closely enough, lead to the most extraordinary depths. Before we close, let us spend a moment with the human beings working on this problem. Because it is easy to think of frontier physics as something that happens in some abstract realm, carried out by godlike intellects who think in 11 dimensions and dream in mathematics. But the physicists working on quantum gravity are people who drink coffee in the morning and get stuck in traffic and worry about their families. They are people who sometimes spend years pursuing an approach and then realize it is a dead end, and they turn around and start again. They are people who experience genuine joy when an equation comes out right and genuine disappointment when it does not. The search for quantum gravity is a human endeavor, carried out with human patience, human creativity, and human stubbornness in the face of a problem that has resisted solution for nearly a century. And they keep going, because the question is worth it, because the universe is under no obligation to be comprehensible, and yet repeatedly, stubbornly, it turns out to be. Reality turns out to follow rules, rules that can be discovered, rules that can be written down, rules that, once understood, give us a kind of power over our situation that no other species on this planet has ever had. That faith in comprehensibility, that conviction that the deep structure of the universe can be understood and not just measured, is the engine of physics, and nowhere is it more tested, and nowhere does it burn more brightly than in the hunt for the quantum nature of gravity. So close your eyes for just a moment again. Listen. Something falls somewhere nearby. The same sound we opened with 3 hours ago. The same apple, the same rain, the same pen rolling off a desk, the same force, doing the same thing it has done since the first moments after the Big Bang. But you hear it differently now. Do you not? You hear in it Newton's 3 centuries of successful equations, beautiful and honest and admittedly incomplete. You hear Einstein's warped space-time, his bent geometry, his beautiful revolution that gave us GPS and black hole images and gravitational wave observatories. You hear the frustrating, productive tension of a universe whose 2 greatest theories cannot yet be reconciled. You hear the ghost of a particle called the graviton that may or may not exist and may or may not ever be found. You hear the wild frontier theories, their strings and quantum foams and emergent landscapes and holographic boundaries and wormholes that might be entanglement by another name. And underneath all of it, you hear the question. The same question Newton refused to guess at in 1687. What is this actually? What is happening when things fall? What is gravity made of? We do not know yet, but we are asking the right questions. For the first time in history, we are very close to asking exactly the right questions. And in science, asking the right question is more than half the battle. The right question, held patiently and pursued honestly, always leads somewhere true. The apple falls. The universe keeps its secret just a little longer, and somewhere someone is getting closer.